Good morning. Welcome to the European Space Agency. This is a media briefing for the first data release for Euclid. My name is Emmett Fletcher. I'm from the Communication Department at the European Space Agency. My job here is to speak as little as possible and really to allow our experts to explain the wonderful things that this amazing mission is doing, and also to remind you of some ground rules regarding this media briefing. As you all know, this media briefing has been carried out under embargo. No data can be shared from this meeting until the 19th of March. That's Wednesday at 11 o'clock GMT or 12 o'clock Central European time. So I think you all know that already. So we will very quickly, and the one other thing is we have we'll go through a presentation, and then afterwards we'll open the floor to questions and answers. Hopefully that's helpful. So just one thing during the Q&A. So afterwards, we need you to raise your hands. So we can mute you in order. If you don't wish to speak, that's not a problem. Please just leave your questions in the chat, and I have no problem at all in reading them out to the panelists on your behalf. So without further ado, I'd like to allow our panelists to introduce themselves. And if I may, I'd like to pass over to Dr. Carole Mundell to start the briefing.
Thank you, Emmett. Good morning to you all, and thank you for joining us on this exciting morning. My name is Professor Carole Mundell. I'm Director of Science here at the European Space Agency and also Head of the European Space Astronomy Centre outside Madrid. And for me, I think this is such an exciting morning to be able to show to you today those first glimpses of this first big science data release. And you'll hear through the session about the mission, why it's important, why it's special, and what you can extract, I hope, for your readers and your viewers from the information that we'll be releasing, as Emmett said, under embargo on Wednesday, which will be released middle of Wednesday. I'll pass over to my two experts. It's my pleasure to have our project scientist and one of our experts from the Euclid Consortium. So I'll pass over to Valeria first, and then after to Mike. Valeria, please introduce yourself.
Thank you very much, Carole, and good morning, everyone. I am Valeria Pettorino. I'm the Euclid project scientist at ESA, ESTEC in the Netherlands. I joined the Euclid effort in 2007, so now 18 years ago. First in the Euclid Consortium, and then in different roles, and then at ESA as a Euclid project scientist. So I'm really excited to be here today to first discuss with you, illustrate to you the Euclid, the first data release. Imagine that, again, we have worked for many, many years on simulated data, and now we are really at the first data release. And I'll pass it over to Mike, who is Mike Walmsley, who is from the Euclid Consortium.
Hi, folks. Good morning. Thanks for joining. My name's Mike Walmsley. I'm a postdoctoral fellow at the University of Toronto and a member of the Euclid Consortium. And it's a big week for all of us at the Euclid Consortium because scientists were always excited to get our teeth into the data. And this is the week that we get to tell you what we found. Those first pieces.
Wonderful. Thank you, Mike. And I think, Valeria, you kind of nailed it there by saying that for many years, all of you who've been involved in preparing for the Euclid mission have been working on simulated data, so what the sky might look like, and getting all of your tools ready. And, you know, today you get to see what the sky really does look like in depth. Sandra, I wonder if I could ask you to share our first slide, please, and then I can take us into this brief presentation for our colleagues who've joined. So, as I say, today really is a new milestone for our Dark Universe Detective, the nickname that we give to Euclid. And to put this in context, for me, this is also a very important year for the European Space Agency. This year we celebrate our 50th anniversary. This European Space Agency was founded in 1975 by the combination of the European Launch Organization and the European Space Research Organization. So really, science has been the backbone of the agency for 50 years. And I think Euclid is one of those missions that that really shows the power of our experts within ESA, working with our scientific community and working with our industry partners. And you'll see a few slides from now on, really the immense collaboration that has brought this mission together. We launched Euclid in July 2023. I joined the agency as new director in the April of that year. So this was my second launch. We launched JUICE just in the April before. Euclid for me, I am an astrophysicist by background, and I know the community has been waiting a long time for this day to come. And so we launched July 2023. We had a perfect launch. We had some engineering challenges through the summer, which some of you may have covered. And I'm very pleased that by the November, we had dealt with all of those engineering challenges. And we released our very first images. This was just from test data that we took during the commissioning of the satellites to show that it was working well. And that November release of 2023, I think, dazzled the world. These were just single shot images, and they were images that had been taken from a day of test data to prove that we'd solved all of our engineering challenges and that science was, in principle, feasible with the mission as designed. We then had a second image release in the May of 2024, and this was really where the scientists who had worked on those first images of November 2023 published a series of 10 papers explaining some of the technicalities and some of the work that they'd done in order to produce those images, and did the first sense of science with those first test images. And then in October of last year, we released the first mosaic. So this is multiple pointings. And that really showed that we were able to stitch these images together, as we will have to do for the full survey, but that was just 1% of the entire survey. And so, as we said, on the 19th of March this week will be the first publication of science data, and you'll get a sense of that as we go through the presentation. In the next slide, we cover really briefly what the purpose of this mission is. And I think the two biggest questions that we ask ourselves as humanity is, are we alone in the universe, and how does the universe work? What are the fundamental laws of physics? And our understanding of the universe has developed over many years. We now understand about 5% of the universe. So the ordinary material that makes up you and I and dust and gas and stars makes up only about 5% of normal baryonic matter in the universe. The other 95% is dark and is unknown. We know it's there because dark matter is gravitating, and it makes our galaxies spin faster than we expect them to, and causes galaxies to pull together in giant galaxy clusters. So we know that this gravitating material of unknown type that doesn't radiate normal radiation is there because we see its effect. We also see that the universe is expanding, but not only is it expanding as predicted by Einstein, but it's accelerating that expansion. And that, I think, is one of the biggest mysteries in modern physics. Why is the universe speeding up its expansion? And the whole purpose of Euclid is really to put those two together, to understand the nature of dark matter and dark energy and how they're coupled in the universe. And you can see here the four big questions that this mission was designed to solve. What is the structure and history of the cosmic web? So this huge structure and the systems that we have in the universe that we think galaxies form at the junctions of. What is the nature of dark matter and dark energy, as I say? How has the expansion of the universe changed over time? And really, this is not only a dark detective, it's also a time machine. So we will look back 10 billion years in cosmic history, because not only are we making these exquisite images, but we also have a spectrograph on board, so we can actually measure the positions of the objects that we study and the speed at which they're moving. And so that gives us a 3D dynamic map, if you like, or movie of the universe. And then ultimately we want to test the laws of gravity, because we can get so far with Einstein's general theory of relativity, which checks out in every test scenario that we've tested it, but it doesn't yet, in its current form, explain the accelerated expansion of the universe. In the next slide, you'll just get a sense of some of the image releases that I mentioned. Again, all of these are available on our website. And a single shot with Euclid actually covers about 2.5 times the area of the full moon. And there are 3 very special features of the Euclid mission. Now, any astrophysicist that you speak to will usually tell you you can pick 2 out of these 3 if you have a telescope and you want to look at the sky. But Euclid, for the first time, combines 3. And these 3 are, first of all, crystal clear vision, or so-called resolution. resolution. So how accurately can we measure features on the sky, and how accurately and clearly can we separate one from another? That resolution is very, very good on Euclid, and also it's very stable across the whole field. So wherever you make a measurement, you understand the shape that you're measuring. This is important for our cosmologists, because if they want to measure whether a galaxy seems to be slightly distorted, they have to know that that's a distortion because of the nature of the universe, not because of a distortion within the optics. So we've shown that Euclid has that clear vision and that it's very stable across its wide field of view. Now, I mentioned wide field of view, and of course, a single shot gives you 2.5 times the full moon at this exquisite resolution. And then, of course, we will now scan across the sky for the next 6 years, about 30,000 of these fields. The final thing, which again, as I usually pick 2 out of 3, but we're giving you all 3 with this incredible mission, is the exquisite sensitivity of the detectors. And what that does is it allows us to detect very faint light. So we can see very faint light very clearly, very systematically and accurately across all of the images, and then take the spectra of those objects correspondingly. And to give you a sense of how sensitive the optics are in this telescope, we had a problem when we first launched the mission. We had a tiny little bit of ice inside the optical camera, and it's impossible obviously to work in the labs at 100% dryness, and so just a tiny little bit of water vapor in there, which we expected, so we put some equipment in there to be able to defrost our telescope. And to give you an impression as to how sensitive the telescope is, the thin layer of ice that we ultimately had, we melted off when we solved, was thinner than a strand of DNA, and that really mattered. It was blocking the light coming from the universe. So that's how sensitive these detectors are. Now we've cleared that vision and everything's working very well. You can see here on this slide just a collage of some of the images and the mosaics that we've released over the last 1.5 years. In the next slide, you'll get a sense of the huge human effort behind this and the incredible collaboration across all of our 23 ESA member states, international collaboration with our friends and colleagues at NASA, in Canada and in Japan. And then, of course, the scientific payload is provided by our member states, scientific institutes and industries, and our 2 prime contractors that really integrated all of this together for us, the Thales Alenia Space Prime Contractor for the construction of the satellite, and Airbus developed the payload module, including the telescope. And so together, this has been a huge effort. Many thousand of scientists pulling this together in terms of the science case and the requirements that is then integrated with the engineering and technological capability across industries, across all of Europe, and our collaborators internationally. And so if we go on to the next slide, we will give you a sense of what you're going to see today. And as I say, this is a tiny taste of what's to come, but tiny is not the right word. And we were just talking before we came online here about how exciting this is for the scientists. And really, they have a lot of work ahead of them in the next 6 years, but it's going to be phenomenally exciting and very, very interesting, groundbreaking work. So here you can see an image of the sky. This was from our Planck satellite, which launched back in 2009, and really gave us this accurate census of the universe. That's how we know 95% of it is dark. And you can see really here just the dust and gas in our own Milky Way galaxy, and the rest of the sky, the 36% of the extragalactic sky, is what will be surveyed by Euclid over the next 6 years. But there are 3 very special patches. These are called the deep fields, where we will take many, many, many observations at these same patches and allow astronomers to drill very deep into the universe and back in time. And so these 3 patches really are, we'll do many passes of these during the survey. But the release we're giving you at the moment is just 1 week of observations and 1 scan of each region. And already within those, Euclid has already spotted 26 million galaxies. So again, it's almost impossible to conceptualize the scale. At the end of this survey, we'll have 9 billion galaxies. 1.5 billion of those will be precisely measured for cosmology. But this gives you a little bit of a flavor. And so now, without further ado, I'll hand over to Valeria to take you through these incredible images and data sets from these 3 deep fields. Valeria, over to you. Thank you.
Thank you, Carole. Indeed, as you said, we are about to release the first data from the Euclid survey. And in these areas, the yellow areas that you have just described, which are the Euclid deep fields. So really the areas where Euclid will look deeper and deeper, passing tens of times over 6 years. And each time we will increase the resolution, we will manage to see more objects farther away, even fainter objects. And these specific areas have been chosen years ago due to different constraints. We need to be able to observe these regions several times per year. Two of them that you see here, the Fornax and the Deep Field North, have been chosen also to be complementary to other observations taken by other experiments. And the one in the middle, the Euclid Deep Field South, is really special because it was really designed specifically for Euclid. There has never been another deep survey looking at this area. So this is really somehow more intriguing. It's also the largest patch of the three, and it's really the one where we can expect even to study galaxies which have never been studied so much in such a detail with such a high resolution. Now, you see here the three mosaics to which I think you already have access. These, together also with a video, will be broadcasted on Wednesday on YouTube and on the ESA TV. And then they will also appear on ESA Sky, which is the ESA platform that allows general public and scientists to really dive into these images and really see a lot of very tiny detail as you zoom in, still with very high resolution. Imagine that in one single shot, one picture, Euclid, as a mean over these areas, observes about 250,000 galaxies, just in one picture, for a total, as Carole was saying, of about 26 million galaxies over the three areas. If we go to the next slide, we zoom in into the Euclid Deep Field South, and we already see first, many galaxies. Each bright point in this image, basically, it's a galaxy. Some of them on the right side in merging. But what's also interesting, I think, in this image is to see that there are some areas, for example, in the central top part, which look a bit emptier. And then some others, like in the center down, bottom part, which instead are full of galaxies which cluster. And this is already a hint of what's called the cosmic web, the fact that galaxies don't fill up space in the same way all over space, but they rather form empty spaces, voids, and they group into filaments, into groups of galaxies, which all together form what we call the cosmic web. Euclid will, of course, observe the cosmic web over 6 years, but already now with this data, it's possible to get a hint and to actually get the first scientific results of galaxies and how they behave, how their shapes and alignments are actually depending on how close they are to these filaments. Now, we, as said, data that will be released, images, videos that will be released on Wednesday. But there's also the first scientific results. If we zoom in even further, we see, for example, now this is 70 times compared to the initial large mosaic, we see a cluster of galaxies. Now this one is located about 6 billion light years away. And if you look closely at the center, next to the bright stars in the foreground, you can already see how the light is deflected. It's curved. This is an effect which is called gravitational lensing. Is one of the main observations, probes that Euclid will use for cosmology and for many other study cases. And it's really due to the fact that the image of very far away galaxies are distorted by the presence of galaxies and even dark matter in between us and the source. So this will be studied, of course, on very large scales by Euclid. But as we will see in the moment, already with this data, we are able to see strong lensing systems, study them, and use them for many scientific cases, as Mike will explain in a moment. Let me also recall that on Wednesday, we will also release 34 papers, scientific papers, with the first scientific results obtained by Euclid Consortium scientists using the data release that we have here. there will be 27 scientific papers really using with the first scientific results, and the 7 reference papers that will describe the processing, which is extremely complex from when we get the data from sky, from Euclid, down to be able to process them, to calibrate them accurately, and to extract scientific information from them. So these papers and first scientific results will cover a variety of use cases in astronomy, in astrophysics, from the strong gravitational lensing that I've just mentioned, to galaxy clusters and the cosmic web, to also the detection of few far away quasars, which are some of which are actually very, very far, even more than 12 billion light years, to the understanding of how the environment and impacts galaxies and galaxy evolution. All this comes with 35 terabytes of data, 1 week of data. I was calculating yesterday that, just to give you a feeling, that 35 terabytes of data is the equivalent of having 200 days of video streaming at the highest quality. If you watch TV on your HDR 4K with 60 frames per second for 200 days, then that would be the equivalent of 35 terabytes, which are the data we are releasing this week. And just to give you also context to what's coming next year we're going to release 1 year of observations. That's more than 2 petabytes of data. So that's the equivalent of watching your finest video streaming on TV for 31 years. Don't do that. But just to give you a feeling of the fact that Euclid has to deal with a very, very large amount of data. And I think this is also significant in the sense that it's complex, obviously. You may have already had trouble just downloading the images or the mosaics or the video on your laptop. So this is part of the complexity of Euclid, and I think it's also illustrated by the fact that approximately half of the scientific papers, which are going to be released on Wednesday, are making use of artificial intelligence in order to help with the data processing. And I think at this point, I will hand it over to Mike Walmsley, who will also illustrate how this happens in practice.
Thank you, Valeria. If we go to the next slide, please. I wanted to walk you guys through some of the images that we're releasing on Wednesday, and this collage is showing just a handful of galaxies from those images. Each one's made up of billions of stars, probably with billions of planets, and each one is unique. Like a fingerprint, they're shaped by how they grew. Because light takes time to reach us, we're looking back in time at how they used to look, and that tells us about our own possible history. For example, the galaxies in the bottom right are merging together, and when they finish merging, they might look something like the ones in the top right. And if you look on the top row, some of these galaxies, third from left, looks much like our own Milky Way. Now, Euclid's image of the sky, perhaps the most detailed image ever made, as Carole introduced with that trifecta of properties the satellite has, will have something like 100 million galaxies with features like these. It's 10 times more than any previous telescope. And for scientists like me, the more galaxies, the better. Such a large sample is necessary to let us untangle all the different factors, influences, supernova, supermassive black holes, cosmic web, dark matter, that together shape each galaxy. And on Wednesday, we'll be sharing the first chunk of what will be the largest ever catalogue of the detailed appearance of galaxies. Now, it's easy to look at one galaxy and describe its features. It's impossible to look at 100 million of them. If I spent 8 hours a day, 7 days a week, it would take me 150 years to look at all of those galaxies. So instead, like Valeria mentioned, we use 2 tools, citizen science and artificial intelligence. Anyone can go to the website galaxiezoo.org, see images similar to these, and answer questions about each galaxy. Is it a spiral? How many arms does it have? And so on. It's a fantastic way to engage people in science. And over the last decade, some 200,000 odd people have volunteered their time to help. We take their answers and we use them as examples to teach AI models to make the same judgments. And then those models can describe as many galaxies as we like. It takes millions of examples to train a good AI model from scratch, but we already have millions from other telescopes. And so for Euclid, we only needed about a month of volunteer effort. We're grateful to around 9,000 people who joined in to create enough new examples to fine-tune our models to work well for Euclid. And that's how these images were picked. These were selected by the AI models. We asked the fine-tuned models to give us examples of galaxies that were edge-on, that were merging, that were spirals, and so on. So by showing the Euclid galaxies to volunteers, then using their answers to fine-tune our AI models, we sped up the time to describe every galaxy in Euclid's images from 150 years to 1 month. The bigger shift comes from being able to fine-tune our models to do all kinds of things. If you go to the next slide, I'm going to show you a second collage that's showing Euclid's view of, as Valeria introduced, a rare phenomenon called strong gravitational lensing. So like she said, massive galaxies, they warp space. They bend light rays, just like a magnifying glass, to reveal distant galaxies behind them, and also reveal something about the nature of the universe in between. You can see, if you look really at any of these images, these kind of twisting arcs, which is where the light is being bent, and that's the distant galaxy stretched out. But they're incredibly rare, because both the massive galaxy in front and the distant galaxy behind have to be just perfectly aligned from our perspective for the magnifying effect to work and to create these strong gravitational lenses. To find them, we used the same AI models as before. We fine-tuned our models to pick out possible gravitational lenses in Euclid, and then we asked thousands of volunteers from the Spacewalk Citizen Science Project to sort through and identify the most promising ones. And these are some of the likely lenses that they found. Until now, the vast majority of lenses have been found by ground-based telescopes. And that's because lenses are so rare that you need big chunks of sky to find them. And we simply haven't had a space telescope that has the area and the resolution and the sensitivity to do that. Euclid is the first telescope which can find large numbers of lenses from space. By the time Euclid finishes, it will have found at least an order of magnitude more strong lenses than all previous searches put together. Just the first 0.4% of Euclid's images, just this 1 week of observations we're sharing on Wednesday, we've more than doubled the number of likely lenses with images from space. And that matters because we can see really important details in these lenses that are blurred out from the ground. So I'm just going to point to one specific example. If you look on the fourth column, third from the bottom, we think this might be an example of what's called a double source plane lens. So instead of one background galaxy being magnified, there are actually two separate background galaxies. If you look closely, and you can see the full resolution version in the press material, there's two outer arcs and then two inner arcs right close to the center of the galaxy nucleus. And that double lensing might let us measure dark energy and the expansion of the universe, in complementing Euclid's weak lensing mission. In principle, these strong gravitational lenses can measure how fast the universe expands, because an expanding universe will define the angle of the arcs, the amount of that stretch. But unfortunately, that looks the same as changing the mass of that foreground massive galaxy doing the bending, which would also change the angles of the arcs. And these, rarest of rare systems, the double source plane lenses, might be the key to solving this, because we know that both background galaxies, the light was bent by the same foreground massive galaxy lens. So perhaps any difference in angles might be caused by the expansion of the universe. And double source plane lenses are so rare that only a few have ever been found. And we think that just this first week of Euclid data, we think we found about 4 good candidates already. And it won't be long till we have enough to finally test if they can measure dark energy. So Euclid's making the most detailed image of the sky ever taken. And in a week, that image is already changing what we know about galaxies and gravitational lenses. But it's also, as a technical challenge to scientists like me, it's forcing us to change how we search images. Thanks to citizen scientists and AI working together, we can ask new questions in weeks rather than years. This is just two brief examples of the science in the making with Euclid. You could, instead of me, have heard from any of the other scientists leading the 34 paper preprints that will be shared on arXiv on Wednesday. And now, or on Wednesday, the data will be public. Anyone can use Euclid's images for their own science. You know, science is collaborative. It's about instruments working together. And I hope that over the next few years, we'll see more discoveries like these, some that we expect and some that we never thought of. Thank you. Hand it back to Carole.
Thank you, Mike. Thank you, Valeria. I hope that gives you a taste of the power of Euclid, the excitement in our science community, and the work that everybody will be waking up to Wednesday afternoon. I'm sure the scientists outside of the Euclid Consortium will be there ready and waiting to go to ESA Sky and see what they can find for their own science cases. And I think also, you know, you have the press materials, so if you now have any other additional detailed questions, please feel free to do so. And I think, Emmett, you're now hosting us for this. Thank you.
Thank you very much, Carole. Yes, indeed, now is the moment we are opening up the question and answer session. I noticed that there's already been some activity on the chat regarding questions. So if you'd like to ask a question, I would be appreciated if you could raise your hand. And then I can unmute. And then once you are given the microphone, if you could state your name and your affiliation and then your question. And if you have a specific member of our panel to whom you would like to ask your question, please do so. Right, actually, so we are now open for the question and answer. I already have a question. Stephanie, I will try. And unmute you, but I can't. So I'm trying to unmute, but I can ask Stephanie's question anyway. So Stephanie, this is a question from, if I find it, sorry, it's from Stephanie Jacquet, who works for the RTS in Switzerland. The question was, is it possible to get the images and the papers under embargo before it's lifted on Wednesday? And I don't have the answer.
They were already sent under embargo on Friday. So if you register to our mailing list, you should have received that. But of course, we can reshare today all the materials, including the recording. Yes.
Okay.
Thank you.
It works. Hi, thanks. Good, thank you very much. And now a question from Govert Schilling, freelance astronomy writer. If we could provide the microphone to Govert. Hello. Could you try your microphone? Not working. I have the question. The question is for Valeria. So the question is, how does Euclid compare to the recently launched SphereX mission? Are they competitive and do they need each other?
Yes, thanks. Thanks for the question. So, of course, it's always good to have multidexers looking at the universe because that helps us to identifying systematics, in particular if they work with different instruments, with different wavelengths, with different resolution. So it's never, for me at least, it's never seen as a competition, but we are actually also collaborating with the group at IPAC in Pasadena, who are also key partners in Euclid. And specifically, SphereX is a mission which has similar scientific objectives, but they focus on spectra, on measuring near-infrared spectra for millions of galaxies. Euclid is a larger scale mission. It includes 2 instruments. It joins the information from photometry and spectroscopy, and it has an extremely high resolution and a very wide field. So for us, it is really fundamental to join photometry and spectroscopy to measure images and from there with lensing and to measure distances and spectra. This is crucial in particular for dark energy and to disentangle the different possible theories that may describe what dark energy is and to test gravity, because the gravity in particular depends on both weak lensing and also on how structures are evolving in time and space, which is described thanks to spectroscopy.
Thank you very much. Next question. So look, where are we? It's from Javier Barbuzano. We will try to unmute you.
Thank you for the conference. It's been very interesting. I'm a freelance journalist, and I have a question for Mike. I would like to know a little bit more about how you use artificial intelligence and computing to find stuff in the data, and in particular, how it's going to be used to solve the cosmological questions of Euclid.
Yeah. So let me deal with each half of those in turn. So we've had astronomers have been at the front of developing AI algorithms for the last decade or so. Been really interesting because our astronomy in many ways is a computer vision problem. We have a very large image, you want to understand it, and we need to do so automatically because of the scale. And Euclid is the latest and highest resolution, highest area version of that. So we're using techniques which you might be familiar with from your smartphone. When you take a picture, it will know if there's a cat or a dog or your friend. We're training artificial intelligence algorithms from a subset called deep learning, and specifically convolutional neural networks or vision transformers. And we are doing them in a couple ways, but the way that I talked about in this presentation is to take real images, to have human volunteers, citizen scientists, annotate very large sets of them, something like 100 million individual clicks, and then to take those models and fine-tune them to specific science cases. So here, measuring the morphology in Euclid or finding strong lenses in Euclid. And we found that by training generalist models, kind of like the G in GPT, we can be much more efficient with how fast we turn this around, because we need fewer new human labels to make the models understand new surveys, new instruments like Euclid. So that's how we managed to measure the shapes of the visual appearance of galaxies and find strong lenses in a matter of weeks from the data release. It's about making generalist, adaptable foundation AI models and then using humans to tune them to specific cases.
Okay. Thank you very much. Next question, if I can have the mic open for Ian Sample. Ian, over to you. Ian? Okay. Okay, then if not, then I go across to Chloe Durand Parenti from Le Point. Would you like to speak or would you like to ask the question? I have it written down here. Maybe it's quicker if I ask it for you. It says, in the press release, you mentioned the use of artificial intelligence and citizen science to classify galaxies and identify gravitational lenses. Could you elaborate on how these two approaches are combined in practice and what specific roles AI and human volunteers play in the process?
Yeah, I think that might be a question for me again. So the fun part about this is you can go and join in and take part yourself. And that might illustrate how it works. So you can either Google galaxiezoo.org or Google Spacewarp's Euclid to join in each of those projects. And the role of the humans and the volunteers is opposite in each of those projects. So for classifying galaxies, we took 100,000 little cutouts, like I showed you in that collage. We showed them to human volunteers on Galaxy Zoo, and they answered a series of questions. Is it smooth? Is it featured? Is it a spiral? How many arms? Are they tightly wound? And so on. And then we took all those answers that they gave us and trained models to reproduce them. So we could show a model a new galaxy and say, what would a human volunteer have said for this? And once they're trained on enough data, the models become technically superhuman in that they're more accurate than something like 5 individual human volunteers. And then we show that all the incredible numbers of galaxies that Carole and Valeria mentioned to those models. And they take over from there and measure the whole survey almost instantly. For Spacewarps, it's the other way around. So instead, we're actually, as scientists, able to simulate what strong lenses look like, because we understand the equations that govern how matter bends light. So we simulated many images of strong lenses. We trained our models to find those. We ran the models through again. We gave them, something like 100,000 cutouts from this first week of Euclid data, and the models predicted which ones were most similar to those simulations we showed, which ones looked most like they were strong lenses. And then the humans were the verification step. So the citizen scientists on Spacebook were asked, does this really look like a strong lens, or is it just perhaps something unusual that we didn't simulate? Something we didn't expect to find, or just in the kind of intrinsic complexity of the universe, there's a lot of weird galaxies out there that can confuse our AI models or imaging artifacts, things like this. So we use the volunteers as a verification stage to filter down the most promising candidates, and that's what created the collage that I showed you. And you can read more about this technical details in the papers on Wednesday that I think you have copies of, the visual morphology paper and the strong lensing discovery engine papers.
Thank you very much. I have the question from Ian Sample from The Guardian. In one of your slides, you list the 4 main science questions for Euclid. Has this new tranche of data provided any hints of answers to any of these, or is that all to come down the line? Thanks.
I think maybe I'll take this and then pass to Mike and Valeria. I don't want to break any secrets. I think what you're seeing is a taste of what's to come. So we don't have the cosmology answers yet. That will be the 6 years of the survey. As Valeria showed, we can already see the cosmic web hinted by the structures. You saw the void, you saw the galaxy cluster. So already in these wider field images, you're starting to see that cosmic web. So we know it's real, and we know that we will map it as predicted or expected by Euclid. The nature of dark matter and dark energy, yet no. The fundamental cosmological parameters that our cosmologists want to calculate and measure and derive from the data, no. They will be derived through the course of the survey. But Mike and Valeria, I wonder if you might want to comment beyond that.
Yes, indeed, as you said, the current results and the Q1 data release is not directly used for dark energy. The first cosmology release would be in 2026 with 1 year of data. This is a preview of which is used, however, for a variety of purposes in astrophysics and cosmology. It's a sort of bonus science that it's really beyond the main core objectives of dark energy and gravity, but which by itself is important for astronomy and will be used for years by the full community. I mentioned before some of these study cases also that we can do also on smaller patches without having yet the full map of the sky. Mike mentioned, for example, the strong gravitational lensing. We saw galaxy clusters, cosmic web. All this is already used to understand the key questions about galaxy evolution and how also the morphology, the shapes of galaxies change depending on their environment and how close they are to the cosmic web. So I think, again, this is a preview, but it's still very illustrative of a lot of science cases that are really important for astronomy and astrophysics and will be used for years.
And I'll just chip in at the end to say I spend my entire career on this sort of foreground galaxies, which are in the way of some of these cosmology questions. So it kind of depends which perspective which questions you want to answer. To me, this is one of the most exciting weeks because we have images already which are of comparable area to a good chunk of the total images Hubble have ever taken in terms of sky area. And we have more strong lenses from space here than we've had ever found before. So it's both a preview and an exciting moment in itself for particularly understanding galaxies, where we can say a lot without needing the full survey. And also as a technical matter, it's impossible to plan in precise detail how we will deal with the technical challenges that come from Euclid data and answering those science questions until we have pieces of it ourselves to play with and work out our pipelines. So from a science point of view, now this lets us know exactly what we have to work with, and that's super helpful.
That's great. Thank you so much. I'd like to pass over now to Catherine Wright. You have the microphone. Just one thing you need to accept, there's a little pop-up that appears you need to accept, otherwise it doesn't open the microphone on your side. If not, we can come back to that in a second. Okay, so sorry, if I go over back to Stephanie Jacquet.
Yes, do you hear me?
We can.
Oh, fantastic. I was wondering if with this release you already found some things that you were not really expecting, like scientific surprises, so to say?
Yeah, perhaps.
I'll hand to our experts. I think Mike touched a little bit on this, on so many of these strong lenses. I know I've worked with colleagues in the past who've painstakingly searched for these things in, small surveys, or they've done ground-based surveys and they've had a hint of something. So I think the scale is one thing that strikes me, but maybe particular surprises, Valeria or Mike might like to comment.
Yes, indeed. I think it's already incredible that they were used for so many scientific applications. I think beyond what we were initially expecting, because there's really so much data already in this first visit of the Euclid deep fields. I think the catalogue of, for example, strong gravitational lensing is one of the highlights. The catalogue also of how to use and shapes of galaxies and how to connect that with cosmic web is also one of the highlights. But there's also measurements of supernovae, for example. There's one quasar that is really far away, farther than 12 billion years ago, which is already included in this first batch of Q1 data. So I think, again, as Mike was saying, it's a preview, but by itself, it's really important for a variety of applications in astrophysics.
What applications do you know already?
Yeah, these ones that I've mentioned, so the study of galaxy evolution, the study of quasars, the study of supernovae, of active galactic nuclei, all these regions at the center of galaxies, which emit very high energy, and how they're connected to galaxy evolution, the identification of how the environment changes galaxies and how their shapes, their orientation with respect to the filaments of the cosmic web, strong gravitational lensing, so all things that are not directly connected to dark energy, but are also important to understand how galaxies form and evolve. Also in faint objects, which on small scales. So we're not really able only to look at very large scales, which at the end will provide weak lensing and information for dark energy. Euclid is also able to look at small galaxies and extract a lot of information from restricted areas in these fields.
And Valeria,
Thanks so
if I may
much.
just add for Stephanie, in our previous releases, we were seeing intra-cluster light, so the light that comes from stars that have been dragged out through the gravitational forces in a galaxy cluster, almost like a kind of a tracer of the dark matter, free-floating Jupiters. And as Valeria said, we're able to see these small dwarf galaxies because they tend to be very faint. They're the building blocks of bigger galaxies. And within galaxies, we're also finding many, many star clusters. So these are the stellar nurseries where stars are born. And I know scientists who work on those star clusters, again, are having to transform the way they do their work. They're now having to predict from the laws of physics what they might see and then confront the data to test their simulations, rather than looking at a single Hubble image and counting a few star clusters. They're having to do these reverse statistical models, very similar to what Mike described on the AI. So again, it's that scale, that discovery, the combination of those three features of being able to see incredibly faint things very, very precisely with sharp vision, back nearby and distant all the way through. Mike, I don't know if you wanted to comment further.
I think that summarizes it very well. And I was just noting another question in the chat that I think there are about if there are more visually appealing objects. And I was just writing that the if it wasn't clear, the collages that I shared are part of the press material that was just shared. So if you scroll down in the embargoed press material, that includes those same collages, and you can highlight, for example, back to the question of, are there surprising things, not just the double source plane lenses, but there are also edge-on lenses, where the foreground lens in Galaxy is a disc, which is sort of face on to the camera. It's just edge onto the camera like this, like a dish. And that's really useful scientifically because it lets us unpick the relative mass of the stars in a galaxy versus the sort of blob-shaped dark matter halo. We didn't know if we'd find those. We didn't know how many we found, and we found plenty. And just by looking at that collage, you can see by eye some of those.
Thank you very much. Catherine, we're going to try again. Are you? So it's going to unmute your microphone. So Catherine, it's over to you.
Hi, I think that worked this time.
I'm
Catherine Wright from Physics Magazine. Are there any highlights or discoveries in the 34 papers that you're particularly notable or you're particularly excited about?
Wow, I think that's quite a personal choice, Catherine. I love them all. I think I'm not going to pick a particular one in public. Valeria, Mike, if you have a favourite, please feel free to say.
I'm not going to pick a favorite, but I still think that I'd say the ones that we decided to highlight, we of course had to make a choice in the press release because there's, as we have already said, many science cases, is really the ability to already have a catalogue of strong gravitational lensing. I think that is exciting because, again, as first in the way in which it was obtained, like Mike just explained, and in the fact that it's really complementary to the weak gravitational lensing that then Euclid will use to tackle dark energy. So I would say the strong gravitational lensing is somehow one of the highlights, also because, as Mike said, it was not obvious that we would have been able to detect so many of them, and seeing them in a collage, a selection of them actually, of the ones which are illustrated and available in the catalog, it's quite impressive.
And Catherine, if I may just augment Valeria's comment there, you may have noticed the press release that we put out in February about the discovery of the stunning Einstein ring. So that was a beautiful example of a strong lens, bullseye through the center of a galaxy. And as Mike had said, these are very rare. So to suddenly go from one where everybody was very excited about the science we could do, and then just a month later, a whole collage of them, I think that really is striking.
Excellent, thank you very much. I have two written questions coming up. So first one from Matthias at Shataka is, is our understanding of dark matter and dark energy progressing thanks to these hundreds of thousands of galaxies and thousands of gravitational lenses? When can we expect studies or discoveries about dark matter? Will it be by studying some of these newly discovered galaxies or gravitational lenses in detail?
Again, let me just open with some preface comments. I think what's striking about these data is the dark matter that we're mapping, right? Mike has shown that all of these lenses show that dark matter is there. We can map some of the luminous matter, but we're actually seeing the distortions of space-time and then the light traveling right through that distorted space-time. Not only are we showing that dark matter exists, we're starting to map out its structures. We're seeing these cosmic filaments. So I think already you're seeing this groundbreaking confirmation of what we expected to measure with Euclid. And then as time goes on, we'll be able to produce very detailed parameters for these individual systems, and then I think statistically across the whole survey. But Mike and Valeria, over to you for more detailed comments.
Yeah, I think it's indeed, as you explained very well, ultimately Euclid wants to do that statistically over billions of images of galaxies to measure those very tiny distortions, which then help us to reconstruct dark matter over the whole sky, and also its changes in time and the distribution in space. Here we're focusing on these specific 3 patches in the map, but it's still extremely useful for dark matter as well. The fact that we are able to detect this strong gravitational lensing effect that really helps us to reconstruct the properties of the dark matter that acts as a lens and therefore distorts these images. Of course, again, there's much more to come, but this is already very useful for that. Of course, next year we will have 1 year of data, and that will cover a much higher scale. So, of course, there will be also results that come from the weak lensing, because we will be able to measure also finer and tiny details in these deformations of the images.
Just to add as well, that there are specific ways, aside from Euclid's one of Euclid's prime missions, measuring weak lensing for understanding dark matter at a cosmological scale across the whole sky, across the whole universe. But these galaxies already tell us a lot about the dark matter residing in each galaxy and how dark matter shapes their evolution. So in many ways, the stars that we see when we look at the night sky, or these images of the galaxies, are just tracers, little dots that are following this invisible dark matter halos that hold them together. I talked about galaxies on the right-hand side of that first collage that merge. Those are being drawn in by merging dark matter halos that we can't see. So by finding these disturbed merging galaxies, we can tell something about how much dark matter they hold by measuring the tightness of their spiral arms, or the length and strength of, I didn't talk about it, but these linear features that go through the center of some of these galaxies called bars. We're learning about the galaxy's dark matter content and how that changes their evolution, how that influences how they grow. For the strong lenses, we can already say, in principle, cosmological results from strong lensing. What we need, the kind of missing piece, is the redshifts of these lenses. And that's where I talked in the end about science being collaborative. So Euclid's image is giving us a world-class targeting list for other surveys to measure the spectroscopic accurate redshifts to these galaxies, and to use those precise measurements to work out things like dark energy, how fast the universe is expanding. So this is a collaboration between Euclid's detailed images and other facilities around the world, which in the next few months we'll hope to be able to share more.
Thank you. I have another text question. This is from Louis Saint from France Info. Is there a major breakthrough in this first release? If so, could you please sum it up?
If there's one is hard, I can tell you one I like. We found a ton of gravitational strong lenses, way more than we expected.
Yeah, I think, Mike, that for me is as we've said, is the standout result. These strong lenses as a tool to map dark matter in galaxies and between galaxies is a fundamental tool. One of the tools, the cosmic tools that Euclid is exploiting, and we're go for cosmology, I would say, with these.
I agree, and we're releasing a catalogue of all these strong lensing systems that then can be used also by the scientific community to dive deeper and use them to extract information about dark matter.
But as we've tried to highlight, there's a diversity of science. When you have an image like Euclid's and you have thousands of Euclid Consortium scientists who have their own interests and goals, what's most interesting isn't really any one, it's a subjective choice which you find most fascinating. It's about the diversity of science being done by all these different people.
And I think if I may say to all journalist colleagues on the call today, those 34 papers are worth glancing over. As Mike said, there are 27 of them that have new groundbreaking science. Our scientists don't get to publish papers unless they're finding new things. So there's lots of new things in there. I think the montages we've shown of the galaxies and also of the strong lenses just give you a sense of the power of Euclid for this science at scale. And, we're now taking things that someone might have done painstakingly for 1 or 2 and had a hint at the physics. And we're now starting to systematize this, and it's still a tiny fraction of what we'll do over the lifetime of the survey.
Thank you. I also have a question from Govert Schilling. Apart from the deep field images, will there also be new images of more visually appealing objects, like the Horsehead Nebula of November 23?
So normally,
So yeah, go ahead, Valeria, please, Yanni.
yes, the images normally have already been shared with you under embargo, and yes, there will be the mosaics in very high resolution, so that really one can also dive in and see very tiny details. There are also some specific zoom-ins. Some are the ones that we showed before, for example, the galaxy clusters, where you already see the lensing effect around many of these galaxies. There's also an image of a view of the Cat's Eye Nebula, a planetary nebula, which is also quite beautiful to see, with a dying star in the center and the shells of very different colors that are around it while the star is sadly dying. That's around 3,000 light years away. And
Okay.
we're also, sorry, and just to add, we're also releasing the collages that Mike shown. So the collection of strong lenses from the catalog and the collection of different shapes of galaxies as they where they appear also in the catalog, and as they were classified based on this interplay between humans and artificial intelligence. And I think actually the collages are also very illustrative of the science which is for which this release is used.
Thank you. I think we have answered all the questions that have been asked. Thank you very much for the panelists. Thank you very much for our esteemed journalists who have chosen to spend their morning with us to explore a lot more about Euclid. Please remember that all the information shared today and all the information we have shared with you previously is under embargo. And the embargo will be lifted at 12 o'clock CET on the 19th, so on Wednesday. That's 11 o'clock GMT. So thank you very much for everybody for your attendance. Thank you very much for the panelists. Thank you very much for the team working in the background. And I wish you all an excellent day. Thank you.